So on to the main event. So many of us have heard so many stories. So many of us have worried, and so many of us have scratched our head and said, what's real and what's not? What's hyperbole and what's data? And it's all surrounding this subject of climate. There's one thing that we can all probably embrace, and that is our climate is changing. That we do know for sure. And sometimes it's important first to look forward rather than necessarily than looking backward, okay? So listen with an open ear, listen with an open mind, and enjoy, because we have a very good speaker today, and that's Professor Rob Gillies. Now, Rob, I'm going to talk a little bit about you before I let you come up here. Because Rob's going to talk to you with a funny lilt in his voice. See, he's not from the Mountain West, okay? In fact, he's not from mainland USA. He comes from this place called Scotland. And so you'll have some fun listening to his discussions as he puts a little lilt to that. He came to us after getting his degrees at the University of Glasgow. He has spent time in the Royal Navy. He's spent time in medical school. He even has spent time on a leave just working in the area of athletics. And you can tell by his build, you'd want him right beside you in those dark areas that you're walking through the city. Rob is a great gentleman on campus, really appreciated both for his wit as well as for his knowledge, for the way he puts you at a comfortable place, but informs you with a lot of detail. He has in 2006, became director of our Utah Climate Center, and as such is our state climatologist and leads a team of individuals researching climate. Today, he is known as one of the United States' leading researchers in climatology, and he is sought out by many, many parts of the country to say, give us a straight sense of direction and how things are going. Operating the State Climate Center at Utah State, he has a network focused intensely on what's happening in the state of 70 weather stations that all link into an electronic database, so he can talk about weather here as well as the greater issue of climate. I've talked enough, Rob. It's time to have you come up and chat with us. Please welcome Rob Gillies, Professor of Climatology.
Can everyone hear me? Yes, I do believe you can. So I'm always very worried in giving talks at 8 o'clock in the morning, because in Britain, people will not even started work yet. We start work at 9 o'clock, and of course, you've all had a big breakfast, and I have a Scottish accent. Not as Scottish as it used to be, and that is sort of the main recipe for snoozing, I think. So we'll probably keep the lights up, and hopefully this presentation here will keep you involved. I'd like to have a little bit of audience participation if I can. This is the Fry Street Quartet, another success at Utah State University. And one of my colleagues in the Climate Center, Rob Davies, is actually part of this. He's not in this picture here. He took it. And they have this project called Crossroads now. And if you ever get the chance to go to that, you should, because it relates music to the environment, to climate, et cetera, et cetera. Also take note of the instruments here, because we will have a little quiz later on. So with that, let's hope everything works. It's always a challenge. The challenge for us in the Climate Center our expertise really now lies in climate diagnostics. We have huge data sets all over the state, as well as all over the world. And analyzing huge data sets is a challenge in itself. And so what we are doing all over the world, as well as in the Western US, are really uncovering climate signals with the purpose of leading to understanding the mechanisms that drive the climate system, and particularly here in the Western US and Utah. And that's hopefully what I'll show you a lot of today. And then from this understanding of the mechanisms comes projections, and that's towards impacts assessments. And again, I hope to show you a good example of that. So we just don't do research. We are actually moving towards trying to provide solutions within the state for climate-related issues, both that are current and for the future. So I'm taking a little prelude here. So we do, basic climate research, which involves, this is actually from our paper in the Journal of Climate. I'm going to show you a couple of these figures later on, but not many, I promise. But this is what we primarily do. And then I'm going to talk a little bit about this. Does anyone, I guess you could read the caption here. What is this? The 83 flood. Why did that occur? Well, I hope to answer that for you at the end of the session, or at least give you an inkling as to why such an unusual event occurred. So climate science, as I see it, is about shorter-term variability and long-term trends. Now, recently in the news, everyone's concerned about long-term trends. Where is the temperature going? What's going to happen to the precipitation regime, et cetera, all over the world. And they tend to forget this variability that is really, really manifest in the Western US. Our climate is much, much more variable than, say, the Midwest or the East Coast. And so we've spent a lot of time in this, and that's what I'm going to show you, some of the work that is associated with that. So let's start with variability. So this is the snow water equivalent, which is for Tony Grove, which is up Logan Canyon. And just want to show you this. So we start off with climatology. So this is what's called the snow water equivalent, which is when you take the snow and you melt it to water, okay? And this is what you would expect from just climatology. Then, of course, if we look at 1983, this is what we had. Okay, it was somewhat more, not significantly more, but it had shifted to melting off in late June rather than what would be normally in May. If I'm blocking away, let me know, please. Okay? Then this is what happened in 2010. So a significant amount of snow. And then this year, this is what we got. So you can just see within that, there's a huge amount of variability in the Intermountain West. And this is a real problem for us when we come to trying to forecast, or when I'm asked by any of the newspapers or any news media, what do you expect this winter? And actually, I said it was going to be dry. And I'll show you why I felt comfortable saying that in a little bit. I'm going to just let the music play out, and I'll just fade out in just a minute. So, for example, this is what we would call the voice, or the instrument that might be generating this, is, say, a violin, and the voice of the violin is characterized by this structure here. And then perhaps this one here might be the viola, and then, of course, this might be the cello. Now, which instruments did you hear there? Were you listening? Did you hear the violin? Did you hear the cello? Okay, what did you notice? Sometimes they were playing very fast. Sometimes they were playing very loudly, yes? Okay, and sometimes there was a slight phase shift between one instrument and another. And then, of course, did you hear a double bass? It's a trick question. No. That was a piece from the Fry Street Quartet. So the voices of these instruments, which have both pitch, tone, all of these things, is analogous, actually, to the climate system. the climate system has a voice. And those voices are characterized just like this, and we have some fancy names for them. So for example, we start at the top there, where things move very, very quickly, and that's called the MaddenJulian Voice. Then we have El Nino, which you've probably all heard of, the El Nino Southern Oscillation. And then we have one called the North Atlantic. We have the quasi-decadal, and the Pacific decadal, and the Arctic, and there are many more, okay? And these are voices in the climate system that have certain periods of time. For example, the MaddenJulian is about 40 to 50 days that it pulses. El Nino is 4 to 7 years. The North Atlantic, 6 years. Quasi-decadal, roughly 12. Pacific, 20 to 50. Arctic, longer than that. So these voices are actually pulsing throughout the climate system, and they affect our climate in very interesting ways. So I'm going to talk about MaddenJulian next, and then I will come into the North Atlantic and also the quasi-decadal and show you how these voices and their transitions and length are important for the climate system. So here's the MaddenJulian oscillation, or voice, okay? And you can see it simply consists of warm, cold, pulsing across the Western Pacific, and you can see it down here. So these warm and cold pools pulse over a period of 0 to 48 days. And what is happening there affects, let's see, what happens in our weather. So what is happening here, the energy is transmitted northward to North America. And so this pulse of energy that is continuously going across and resetting every 48 days is sending energy northward and affecting our weather systems. And this one is particularly relevant because it's responsible for our inversions. Our strong inversions that we have, okay, that last upwards of 10 to 20 days are a result of the MaddenJulian voice in the climate system. And we've published on this. So what it ends up doing is setting up a persistent high pressure over the western US that just stays there. And that traps all the pollutants, as you can see, that we release in the valley. And you can really definitely see it there. We've just published a paper that shows that not only is the MaddenJulian oscillation important, but actually the North Atlantic oscillation, which is this 6-year pulse that comes out of Greenland, is important here too. And what happens, well, what we've shown is the MaddenJulian oscillation sets up the inversion for a particular year. Next year, it does the same, but a week later. And then the next year, a week later, all the way up to 6 years. And then it resets back to the initial time and pulses again and again and again. So this is 2-phase pulses, one coming from the tropics and one coming from the Arctic, that are interconnecting and affecting this kind of weather system that we have. So it's quite, so this is, I guess, is just the point of analyzing these signals in the climate system and then finding out what the mechanism is. So for example, in this case, we can say, we can actually forecast in the climate center now when that high pressure is going to come, when it's going to start, and how long it will last, okay? And we've been very successful at doing that this last year. So that's taking research through to applying it in some context. The next one, this is a little tricky. This is the quasi-decadal oscillation. So this is this 12-year oscillation. So what we have here initially, if I can, is sea surface temperature, again in the Western Pacific, in the tropics, and the yellow is hot to cold. And I have a little animation here to help you understand this. If I go from there, from a crest to a crest, that distance is about 12 years. So this oscillation, this voice, lasts 12 years, okay? Now, what is very interesting about that is that if you go from a crest down halfway, that's about 3 years, okay? So you're transitioning from warm to cold. 3 years from that transition from warm to cold, guess what? The precipitation peaks in Utah. So we have a 3-year phase lag between the sea surface temperature and our maximum precipitation here in Utah, okay? And then, even further, if we look at a peak of the precipitation, again, this is 12 years from peak to peak, follow that halfway down from high precipitation to low precipitation, and guess what? The Great Salt Lake elevation peaks there too. So that's really quite interesting then, because now you've got a connection between the tropics, or precipitation, and the Great Salt Lake elevation, all of which have a lag of 3 years. And when we first discovered this, and that was the first paper that we wrote, that I wrote as director of the Climate Center, we thought, can we use this as a predictive tool? And sure enough, okay, we can, and I'll show you that in just a sec. But now, of course, what I've taken you to is 2012, 2013. Okay, we know that this drives our precipitation in northern Utah. And so when I was asked by the newspapers and the media, what's it going to be like this year or this winter, I said, high likelihood it will be dry. And this is why, because we're in this dry phase in 2012, 2013. And of course, we always have problems doing that because, remember, the key word is variability. So we can really get snookered. You know what snooker is, yes? It's the British version of, what do you call it? Pool? Okay? You can really get snookered because of that variability. So next year, even though we're in this dry phase, we could still have a high snowfall amount. But in general, over the next 6 years, we're in a drought phase, okay? And we will have some internal variability. Now, of course, taking this data, the sea surface temperature, and the precipitation and the linkage between the two, we were able to forecast the Great Salt elevation, this, out to 8 years. And just let me show you here, we have water level, 1850, that's when you actually have data of the Great Salt Lake elevation out to present. The black is the observations. Here's 83, okay? Then we combine the two time series of precipitation and sea surface temperature, and you see that here in the red, and here's our projection here. But the most important thing about this prediction or projection was it went out 8 years. Prior to that, people could only go statistically out 4 years. So combining the two time series and also knowing the linkage between the Western Pacific and our precipitation regime allowed us to go out 8 years. But more than that, it actually allows us to forecast the turnaround points, which could never be done before. So that's where, as director of the Climate Center, we've taken our correlations and predictions, our mechanisms and predictions, into a framework like this. So now let's look at some trends. Let's look at temperature trends, and let's look global first. This is particularly interesting. This is the temperature anomaly and the frequency of occurrence. So this is global temperature. So this is what's happening within the world, okay? And you get a distribution like this. And what this, based upon the historic data, this is the average. This is what you would normally expect the temperature to lie within this distribution. What has been happening to this distribution over time? You can't quite see the years. Yes, you can see the years marching in here. Let's look at that again. So we've shifted the normal, what is normally the case, into a new normal, a warmer state, right? And we've shifted it dramatically over here. So the planet is getting much, much warmer. And where this is really seen and manifest is in the Arctic ice volume, which is here from 1979 to 2012. So we have millions of square kilometers here, and we have the year here. This is the seasonal ice sheet, Arctic ice sheet, as it grows and recedes up here in September versus here. This is 1979. Here it is in 2012. There has been an 80% decline in the Arctic ice sheet as a result of that shift in the distribution, temperatures warming up over the whole of the planet. And the Arctic is the most sensitive, and that's where you really see the signal. Just to give you some perspective on that, here's a video. So it has shrunk from this historic average of 7 million square kilometers to 4 million square. So the black here now to here. To give you another perspective on that, a Utah perspective, it's not equal to 1 Utah, it's equal to 15 Utahs. That's how much ice has been lost in the Arctic, 15 Utahs, which is quite dramatic. What about Utah? Well, here's Logan. Here's historical data, observations. You can see the variability, and actually you can see the quasi-decadal oscillation in there, okay? And there's a significant increase here from about 1980 onwards. There's been a warming. Let me squeeze that up for you, like this, just to show you the extent of it. Not trying to trick you here. You'll see why I'm doing this in a minute. The important point is the slope of the line, right? The rate of increase of temperature. So that's Logan. We go around the state a little bit. You'll see that the global mean temperature is also manifest here within Utah, but to varying degrees. I can give you a perspective on that. If we look from 1950 to 2000, here's Moab, which is 1.4 times the global average, all the way up to Bluff, which is 3.8 times the global average. And you can see why I did that slope, because you just need to look at the slope of the line to see where the greatest increase has occurred around the state. So the energy is redistributed differently all over the state based upon the global energy balance. So that's where we lie. How about precipitation? Well, this is interesting. We're actually getting more precipitation. We're wetter, okay? But less of it is falling as snow, okay? But more as rain. Here's snow depth, for example, from 1950. So this is from the paper. I'm giving you a little bit of science now, okay? It's just not my word. It's data that's published, okay? And you can see the variability, but you look at the trend line, the snow depth has been decreasing since the 50s, okay? How about snow cover? Well, this is what we were used to seeing in the past, agreed. Well, this is what's happening, okay? Again, the snow cover has been decreasing, and you're seeing more of that, okay? And the interesting one is the snow-to-rain ratio, where you actually take the amount of snowfall and you divide it by the amount of rain, okay? So if you're getting more rain, right, that means either this is decreasing or this is increasing. And so you can see that the snow-to-rain ratio line is, again, decreasing, i.e., proof in the pudding, less snow, more rain. But then the winter storms have become less frequent. This year was a classic example of that. We had, what, 3, 4 major storms? And that was about it, okay? But that's the norm. So these systems here, with the cyclone center is here. You've got the cold front lying down here. As it comes through, it dumps snow or rain. But these systems are becoming less frequent. Here's the data. So here's the precipitation, the frequency, sorry, over from 50s up to present. Precipitation is going down. Snowfall is going down. So precipitation, okay, is going up, right? But the frequency of storms is going down. Is that a conundrum? What must be happening? Each storm is dumping more precipitation, and it's doing it in a more intense way. So we're getting more intense events, less of them, but they're dumping far more precip, but more as rain. So what does the future hold? Well, to look at the future, up until now I've shown you empirical statistical evidence. Would you be happy extrapolating that into the future? Some might, okay? What we like to do as climate scientists is we build models. And we always have a problem with models. And I'm sorry Miss America is here in many ways, because the next thing I'm going to show is that this is what people think models are. Climate models are not Miss America, I'm sorry. They're actually very sophisticated physics and mathematical models, of which here are a few equations, okay? So what about the projection trends that come from these models? I'm going to show you one, hopefully. This is what's called the NARCAP, the North American Regional Climate Change Assessment. I've got the snow to precipitation ratio here and temperature on the right-hand side. Let's look at temperature first. Okay, so we've got the year here from the 50s up to the 70s. Here are the observations in the black, and here's the trend line associated, temperature increasing. And here's the UK model from the Hadley Centre, which projects, lines up rather nicely actually with the observations, slight warm bias, but its projection is that. In other words, temperatures are going to continue to increase, okay, within Utah and within the world for that matter, under the CO2 increase scenarios that we have. You would expect to see this manifest in the snow to rain precipitation. Here's the observations, and the model shows that that is definitely going to, or it's implying that that's going to be the case into the end of the century towards, say, 2070. So you go from there, you really see that our regime is going to change from snow to rain in a big way. Where I can really show you this is with this scenario. So this is from a particular climate model. It's going to show you the spring, March, April snow depth for the A2 high scenarios, which is really the current scenario that's going to run. It's going to run from 1850 to 2100, and it's a 40-year running average. So from 1850 up to about 2012, you're going to see observations. After 2012, you're going to see the predictions of the model. And here's what it shows. So here's the date. As you can see, here's the snow depth. And of course, you can focus in on our state. So we're still in observational mode. So it's still observations. You're basically seeing the data that I've shown you, okay, in the presentation so far. You see that? Now we're moving into projections. So that's where, according to the models, where we're going. So that is really quite sobering. So that's just visualizing the previous information that I've shown you. Why should we care? Well, here's Utah groundwater dependence. The color here is the percentage dependence on groundwater for public supply for 2005. And you can see that over the whole of Utah, except for Salt Lake and Emory, that groundwater dependence is extremely high, almost 100% in every county, except for, as I said, Salt Lake and Emery. They rely on reservoirs for their public supply water. Now, why does that really matter? Well, the groundwater, okay, recharge, relies on snow. It relies on a snow melt that is very slow. In other words, temperatures matter. So as temperatures increase and that snow melts faster, but you're getting more rain than snow, you can compound the factors yourself, and you can see that the groundwater recharge will be marginalized given the change in the hydroclimate. And then just linking that over into the reservoir recharge, it's affected by temperature timing and associated runoff. So if you get an early melt very early on, you will overfill your reservoir, you'll have to drain it, and when you'll lose all that water that you would hope to store for later on in the season. And then with higher temperatures in the summer, you're losing a lot of water through evaporation and also evapotranspiration. So of course it really does imply that there are consequences, and society will have to change its practices if those scenarios prove true. And with an increasing population, there are even more factors in the equation that have to be considered. And now we come back to 1983 and State Street being State River. What do you think happened? Anyone? Climate Voices had a play. We had the quasi-decadal oscillation, we had the Pacific decadal oscillation, and we actually had a 120-year oscillation. We don't know what caused it. All came together in phase and sent a really, really loud signal for 3 years into the western US. So we had 3 years of extremely high precipitation, and you see that there's a 3-year phase lag, and guess what? This happened. And I believe with that, the symphony is over. Thank you.
Rob, will you take some questions?
Of course.
Okay.
Yes.
Please tell us a website where we can access your information, or a Weather 101 book on the oscillations.
It's actually fairly new in climate science. I'm actually going to a conference tomorrow in France. The Europeans are way ahead of us in this science, actually. And so it's all just coming out in the last 3 to 4 years, actually.
So cheap.
Well, but we do have, we will post information on our website, which is, I know I'm supposed to put this up at the end, is that right, Mark? Mm-hmm. But I could, the website is just climate.usu.edu. Okay.
Gillies, tell us what sort of bodies you have with state decision makers, policy makers, lawmakers.
In the last 4 years, it's varied a lot. I gave a presentation to Governor Huntsman and his executive on the knowledge base at that time. I've also given presentations to Alan Matheson. Alan Matheson, is that right? Jim Matheson. Alan is there. See what happens. And I've given presentations to the Utah Bar Association, to the National Bar Association, so that there have been various avenues through which I've presented a lot of this material. Although a lot of this is actually new, that work was just published last summer. The real study of Utah's climate.
And then as far as the business community, the ski industry, all those folks, have they heard?
They probably heard of me, but they haven't heard from me per se. Some industries at Jim Matheson's presentation, Connecticut was there, for example. So it has varied over the years, but I've never, this is a rather disturbing scenario for the ski community for sure. They'll always have snow at a certain point at higher elevations, But you've probably seen how the elevation snow has drifted over the years higher and higher. And so, you know, they'll potentially have to make changes there to make snow rather than rely on snow per se.
And do you have colleagues in the other western states like Colorado, Wyoming, Idaho? Are they on a similar path, or are you ahead of them?
Yes, they are on a similar path. Yeah, they are. They're, there was a lot of trepidation about 4 or 5 years ago. For example, I gave a presentation at the Utah Water Users Association in St. George, and Representative Noel was in the audience, and I was extremely nervous. And he stood up at the end and, you know, basically talked about the resolution that they passed that year, that saying climate science was debunked. It was nonsense. And we had a long chat afterwards. And it was very nice, actually, I have to say.
Question to the left.
To the left, to the right. Dave, I'll come to you, Dave, after. I recognize your picture. Yes?
I have to ask you this question. Do you believe there's an underlying reason for what you've observed in climate change?
The science dictates that it's carbon dioxide, methane, greenhouse gases, including water vapor, are the result of this. And that's based upon a plethora of data from the ice cores, from the corals, from sediments in the Great Salt Lake, for example. So I'm afraid to say that's the truth. Dave.
I have a question related to it too about our politicians. I think many of you know Representative Stewart is the chairman of the House Subcommittee on Environment. 2 weeks ago, he introduced a discussion about climate change. In the introduction, he said that climate change, global warming, has stopped in 1998, and that the models do not predict this stop. And so I wonder if you would comment on that, particularly as I see the models. I'm not a scientist. It looks like the models are pretty complex and probably pretty robust. Again, he kind of said, hey, the models failed us because they failed to predict this stop of global warming.
Well, the IPCC, the Intergovernmental Panel on Climate Change, did not say that it was going to be a continuous increase. Okay? They said there would be fluctuations. So yes, the temperature has gone up, and now it's leveling off a little bit. The reason for that is all the energy, okay, is going into the oceans. So the oceans are acting as a huge reservoir for that energy. So we've reached an equilibrium point, and as temperatures go up in the atmosphere, they then come down because it goes into the oceans. Then we'll reach a new equilibrium, and the temperatures will go up again. Now, the models are really quite sophisticated, and the recent iteration of models, which will be analyzed later this year, which is called the CMIP5, the Coupled Modeled Intercomparison Project. Prior to that, it was CMIP3. Those are now actually coming out. And they're very sophisticated. It's not just the atmosphere, it's the oceans, the cryosphere, the biosphere, all components. It's a very complex system, and there's lots of feedbacks in the system. But the climate scientists never said, you know, it's going to forever, you know, temperature's going to increase. There always has to be an equilibrium point, and that has been reached where the energy is going into the oceans. And that is even more disturbing. I don't know if you know, if you want to know the reason why.
Tell us why.
So at the moment, we have almost reached 400 parts per million of CO2. The normal maximum in the last million years has been 280 parts per million. So we are way out with what we call natural fluctuations of CO2 in the atmosphere. And CO2 in the atmosphere is important. It keeps our planet warm. Otherwise, the planet would be very cold. So we've reached 400. If we get to 800, and it looks like that's where the world is going, okay, a lot of that energy is going to go into the oceans, okay? I mean, it won't be just a straight atmospheric temperature, you know, incline. A lot of energy will go into the oceans. If at that point, say 50, 60 years down the road, society says, okay, we've had it. The temperatures are so extreme now, and there's so many extreme weather events that are causing big problems on the planet, we now have to get CO2 down by whatever means the society decides to do, and say they manage to bring it down to 400, the temperatures won't fall, because all the energy stored in the ocean will come back out into the atmosphere. And the time lags in the ocean are 1,000 years. So potentially 60 years from now, if things get critical, you get CO2 down, you're still going to have that temperature for potentially 1,000 years. And that's going to be driving the climate system. And that's because the ocean has huge time lags in it. The atmosphere has time lags of, weeks, months. You see the oscillations there, upwards of 50 years. The oceans have time lags of hundreds and thousands of years. So that's potentially, I'm Mr. Doom and Gloom, I know, but, but that's the science as it stands at the moment. Yes, Kirk?
I've heard that for every 1 degree of temperature increase, there's a 10% drop in food production on the Earth. Have you heard that?
No, I haven't heard that, but I've heard similar statistics. We do have a project in Nepal, which is on climate change and livestock. And what is really, really interesting about places like Nepal is their resilience is not as good as the Western world. So they are very, very vulnerable to fluctuations in the climate system. And if it shifts, they can't cope, right? But I hadn't heard that particular statistic. Yes?
Is it possible to run the model backwards?
Yes.
Try to figure out, like, it appears at the end of the first millennium there was a significant drought in this area.
Right.
The demise of the ancestral colon.
Right.
Can you see what variations in the cycles came together to cause that?
We do run the models backwards. Well, I don't. I just use the model data. But the modelers do run the models. They're called hindcasts. And they do that to verify the observations, for example. And then they could go back in time. And then they use, surrogate data like dendrochronology, ice cores as temperature measurements, and then see if the models can match that too. So yes, they can do that, but they don't capture everything. The models, I don't want you to go away with the perception that the models are perfect. They're not. They're evolving, but they're evolving at a huge rate. I mean, there are like 30 models all over the world, and they're advancing very, very quickly. And we realize there are limitations. We don't use the climate models to say it's going to rain this amount here. We simply use the climate models to say what is going to be the trend, right? Because the precipitation amounts, for example, we can't even do that with weather. Okay. Paul.
What about tree rings? Have you looked with those to verify in hindsight?
Well, I do have tree ring data, not in this presentation. Mark made me take it out. So we have tree ring data from the Uintas that goes back about 700 years, okay? And if you look at that tree ring data, this last century, this last 100 years has been incredibly wet. And we've had, 6 droughts? And if you actually look at those droughts, they haven't lasted very long, maybe 4 or 5 years, and they haven't been very deep in terms of the amount of precipitation. You go beyond that, back in time, the droughts have been much longer and much deeper, right? So we've actually in Utah gone into a new state, and that actually poses a very interesting question for us because we've gone into a very wet period. Are we in a stable wet period, or potentially could we go back to that? Or you could pose the other hypothesis that global warming is actually good for Utah because we're getting more precipitation, albeit coming as rain rather than snow. We don't know the answers, and we're not quite sure actually how to answer those hypotheses.
Rob, in the far back corner.
Yes.
Hi. It seems like a lot of the models that look at Earth globally, they look at predictions of ice and things like that. It's always worse, or we're at the worst end of the model, so the models show a range. And then every time the actual, when we get to 2012, 2013, the observations are at the worst end of the spectrum. I'm wondering if the models that we have now, the ones you're talking about, like additional layers of information, are going to help us
So, you know, there are significant, I mean, the error bands in these models are rather large. Again, you're really wanting to look at the trends rather than the errors associated with them. Does that make sense? So I'm not sure what you mean by we're always at the worst end of it.
The predictions showing decrease in ice specifically.
Oh.
We're always beyond what they thought was called the worst case scenario.
Right, that was a big surprise for climatologists. It's a little complicated, and the models didn't capture it, you're right. If you had gone back 10 years, they would have said the Arctic ice sheet will not be gone until 2050, right? The latest projection is 2017. And the reason for that is the feedback mechanisms in the system are not accounted for, because a model has the climate models take a huge amount of computation power, and therefore they have a very big spatial grid. You know, so you have a 200 by 200 kilometer, and you have to account for processes within that grid. That's a problem. That's changing, right? But that was the case in the past. Now, we always said, well, the trend is the Arctic ice sheet will decrease, but the rate was not correctly projected. And the reason for that is the positive feedback that's associated with ice disappearing, which is highly reflective to sun, and then ocean, which is highly absorptive of sun. And so as the ice disappeared, you got more ocean. It absorbed more, believe it or not, solar energy, caused more evaporation into the atmosphere. Water is a greenhouse gas, and you got a runaway effect all the way down the line. And that wasn't captured in the climate models. But what is happening now are the climate models are, because of the change in computing power, we're able to get down to finer resolutions. But what else is happening is we're coupling regional scale models that are forced by the climate models. So we can actually get down to watershed level sort of resolution. So it's an evolving situation, for sure. Yes?
As you talk about the different oscillations and frequencies of the oscillations, such as the longer ones in the ocean, are there any similar oscillations that take place with like energy output from the sun that kind of impacts these as well?
Yeah, there's an 11-year solar cycle, right? And actually you see that in the QDO, okay? So there is an 11, 12-year cycle in solar output, right? And there are other situations that come up randomly as well. But I'm no expert in that, for sure. But, you know, there's a lot of people would say, well, it's the sun that's driving the increased temperatures on the planet. It's not. The actual solar output, the total solar output, is actually decreasing. It's in that phase, right? So, but there are cycles in the sun, yes. And there are natural cycles that are associated with the orbits of the planets as well. But they're huge cycles. They're 30 years, 300 years cycles. And they have been the cause of changes in climate in the past, right? And associated or coupled with feedback mechanisms. So maybe that was maybe more than you wanted to hear. Yes?
Water districts, it seems like we've created an infrastructure based on snow to feed our cities, reservoirs, et cetera, et cetera. We now have dust on snow.
Exactly.
We have rising temperatures. We're going to have less snowpacks to these reservoirs. And then all the infrastructure that comes down to the reservoirs. And then the aquifers, it sounds like it's happening fast enough that it might be reasonable for a water district in a 10-year plan to start thinking about
and they are
going to adapt their infrastructure. Are they doing that?
They're doing that. They are starting to do that. There's starting to be conversations about this. So it essentially comes down to a risk management strategy, okay? To what extent do we see that these observations will continue into the future? To what extent do we rely on the projections of the models? And so you provide a leveled risk management strategy, but they are doing that.
So should we start capturing rainfall off the top of our roofs?
They just passed a law to do that, didn't they? This year, did they? I believe they did. Yeah. Yes.
As we look at the Earth's history, it seems that we've gone through ice ages and periods of non-ice. How is that, or do our models predict that? Are we looking at an ice age in the distant future, or are we going to have the tropics down at the South Pole again?
Okay, that's a big question you just asked, right? What you're saying is climate has changed in the past under natural forces. And those natural forces are, as I've said, all been due to orbital parameters. They're called Milkanovich cycles, okay? And so they've tipped either the tilt or the orbit around the sun in different ways, which has changed the energy balance of the planet. Now, that's not enough to shift the climate. It becomes really, really intricate because once you shift the energy balance, there's a redistribution of that energy throughout the planet. And it's kind of like in your house, for example, you say, well, I'm willing to spend this amount on my energy per month, agreed? But you then choose how to redistribute that energy throughout your rooms. So you might make one room warmer, you might leave your basement cold because you don't live there or whatever. And that's exactly what happens with climate. As the energy balance changes, the redistribution changes. And as that redistribution is very subtle in many ways, then that's when ice ages start to happen. Because the redistribution of energy, both within the atmosphere but also within the oceans, changes. And then that, say, for example, allows a little bit of ice to develop, right? Then the ice reflects more solar radiation. That allows a little bit more ice. So you can imagine it gets very, very intricate. And there are these huge cycles, you know, from 100,000 years to 30,000 years, then within the oceans or whatever, all interconnecting to produce things like the Little Ice Age or whatever. But at that point, the carbon dioxide was still less than 280 parts per million, right? Because it was changing too as it was being absorbed in the oceans versus being released into the atmosphere. So it's very, very intricate. It's a big question, but it's a good one.